Captopril, whose structure is shown below, is used to treat high blood pressure and congestive heart failure. Which statement best describes the stereochemistry of captopril? So a lot of pharmaceutical agents have chiral centers. So what we want to do, we're giving some options here. The first one is that this would be an achiral molecule. And the other options are considering that we have two stereocenters. So the first thing we need to make sure that we're comfortable doing is looking at a molecule and determining where the stereocenters, if any, are, right? So if you look at this first statement, just to make sure we're clear on our definitions, achiral would mean not chiral. So this is either going to be a molecule that does not contain any stereocenters, or no chiral carbons, or potentially it has chiral carbons and it has a plane of symmetry, okay? And so that would be a special case where a molecule that has chiral carbons but has a plane of symmetry that renders it achiral. We describe that as being a meso compound. And a quick glance at this molecule should tell us that everything in it looks pretty different. So we're not dealing with a molecule that has a plane of symmetry. So it could still be achiral if it doesn't have any chiral carbons. So we want to make sure that we understand what is a chiral carbon and how do we find it when we're looking at this molecule. So a chiral carbon is one that is sp3 hybridized and has bonds to 4 different groups. So with bonds to 4 different groups. And that's not just 4 different atoms, they have to be different. So an ethyl group and a methyl group, for instance, are different. So the other way to think of that is to say that they're the same, they have to be 100% identical, okay? So when we're looking for chiral carbons, a quick way to assess a molecule, since it has to be sp3 with bonds to 4 different groups, is we can make some eliminations here. So we could eliminate from even considering any carbons that are not sp3 hybridized, so those would be sp2 and sp carbons. We don't have to look at those. They don't have 4 bonds, or they don't have 4 different groups, I should say, because you're gonna have 4 bonds, but some of them have multiple bonds. So you can eliminate any of those, and you can eliminate anything that's very obviously a CH3 or a CH2, because when you have multiple hydrogens, you do not have 4 different groups. We can eliminate any CH3s and CH2s, okay? So if we take a look at this molecule then, we see we have these carbonyls we don't have to consider. We can see these CH2 groups that we don't have to look at. That CH3 we don't have to consider. Our chiral carbons are here and here. So the other carbons, the ones that I didn't even look at, are either sp2, these carbonyls, or these are all CH2, 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 and this is a CH3, okay? And I'm actually going to draw in the CH3 because we're working with this chiral center. It'll help us to see what's there. So we know now that there are 2 stereocenters. So now the question is going to be about the configuration. So they might both be R, one might be R and one might be S, or they can both be S. So we need to look at both of these chiral centers and assign the stereochemistry. So if you look at this top carbon atom, we can see 3 bonds. The 4th bond must be to hydrogen. Since we see bonds in the plane and one sticking out at us on a wedge, that means our hydrogen must be on a dash bond. So there it is. So we want to assign the priorities to the 4 different groups. So we can see priority number 4 is definitely going to be the hydrogen. It's going to be the lowest priority because it has the lowest atomic number. And conveniently, it is facing away from us. This will make it easier for us to assign the stereochemistry. The next thing we need to do is we need to decide between these carbon atoms because we have carbon, carbon, carbon. So it's the same at that first point of connection. So we now need to see what are those carbon atoms attached to. So this top carbon atom has 1 bond to carbon, 3 bonds to hydrogen. This carbon atom has a bond to sulfur, a bond to carbon, and 2 bonds to hydrogen. And finally, this carbon atom here has 2 bonds to oxygen. That's how we count a double bond. We say 1, 2 bonds to oxygen, 1 bond to nitrogen, and 1 bond to carbon. So when I'm listing out these bonds, notice that I'm listing them in decreasing atomic number to make it easy to compare. So now what I'm comparing is carbon to oxygen to sulfur, and we have a difference here. So sulfur is the heaviest of these. It is the highest atomic number, so this is going to be priority number 1. Oxygen will be next, so that's priority number 2. And carbon finally would be priority number 3. Since the lowest priority group is already oriented away from us, we can simply draw our arc from 1 to 2 to 3. Notice that it is counterclockwise, so this top chiral center is S. So we can now eliminate the option where they both are. Let's take a look at the next chiral center. So if we look at this one, we can see that we have 3 bonds. So the 4th bond is understood to be hydrogen. Since we have a bond in the plane, a dash bond, our hydrogen then is on a wedge. So that's where our lowest priority group is. Hydrogen, whenever you have it, is the lowest priority because it's only atomic number 1. And so that's going to be priority 4. This is facing away from us. This is exactly the opposite of where we want it to be. But that's okay, because what we're going to do is we're going to assign our priorities, we'll draw our arc, and then we'll flip it, because it's as though we're looking from the wrong side. So if we're looking from the top and it looks clockwise, if we were standing on the other side, it would actually be counterclockwise. So let's assign our priorities. So we have nitrogen, carbon, carbon. So nitrogen has a higher atomic number, so that's going to be priority number 1. Carbon and carbon. So now we have to do what we did up here and look at the bonds. So this carbon has 1, 2, 3 bonds to oxygen and 1 bond to carbon. The carbon down here has 1, 2 bonds to carbon, 2 bonds to hydrogen. So again, listing these out in decreasing atomic number will make the comparison easy. So we're comparing oxygen or carbon to oxygen. Oxygen has a higher atomic number. So that's 2, and this is 3. So when we draw our arc, this is clockwise, so it looks like it's R, but we're actually going to flip it to be S. And that's because the lowest priority group is on a wedge. So we're looking at it this way, but if we can imagine ourselves standing behind the plane of the paper, we would actually see that being counterclockwise. So these are both S. So that means that D, the 2 stereocenters in Captopril, and they are both S.